Hello, we will move on to problem solving session 3. This will be module 31 of the course on application of spectroscopic methods in molecular structure determination. We will continue to use the data from infrared spectroscopy, mass spectrometry, proton and carbon-13 NMR spectroscopy for solving simple organic structures. This is problem number 6. The first 5 problems were in module 29 and 30. So we start with problem number 6 in this particular module. Surprisingly, the molecular formula information is not given in this problem. In other words, we have to deduce this information possibly from the mass spectroscopy data. So this is an example of a simple problem where the molecule is a fairly simple molecule. Molecular formula is not known. We are going to deduce even the molecular formula from the spectroscopic data that we have. So instead of starting with the IR spectrum, which we normally do for problem solving, let us start with the mass spectrum in this particular problem. This is a mass spectrum of this compound. The one that you need to immediately identify this particular pattern, which is a triplet pattern with the mass unit, two mass unit difference of 249, 251 and 253. And this should immediately tell you that there are 2 bromine atoms present in this molecule. Only presence of 2 bromine atoms will give you a 1:2:1 triplet of this type in the molecular ion region. First of all, we have to assume that this is the molecular ion of this compound, because that information is also not given. Although it says M plus here, we cannot be very sure unless the M plus is mentioned here. We cannot be sure the highest ion weight peak is the molecular ion peak. The triplet like peak with 2 mass unit difference definitely confirms the presence of 2 bromines. In addition to that, if you look at the molecular weight, they are odd mass 249, 251 and 253. So the odd molecular weight seem to tell that the odd number of nitrogen must be present in this compound. And in addition to that, you also look at the molecular fragmentation. The molecule fragments by losing 2 bromines to give one sequentially, one after the other. It loses 2 bromines to give 91 as the molecular the fragment peak here. In other words, 249 minus 79 minus 79, which is a loss of 2 bromine units, correspond to 91. In other words, 253 also can be taken. If you take 253, it will be loss of 81 isotope of bromine, another 81 isotope of bromine corresponding to 91. So the 91 peak seems to be indicating that the fragmentation is by loss of the bromine. So we conclude from the mass spectrum that there are 2 bromine atoms and 1 or odd number of nitrogen atom present in this particular system. Now, having thought about the presence of nitrogen from the mass spectrum, one has to look at the infrared spectrum carefully to rule out or confirm the presence of the NH stretching frequency to check for primary or secondary amines that may be present in this particular system. Straight away you see the NH stretching frequency. There is a nice doublet that is seen here, which confirms the presence of an NH2 functional group in this particular case. Also, there is a fairly intense peak around 1600 inverse centimeter, which corresponds to the carbon-carbon unsaturation stretching frequency, carbon double bond carbon stretching frequency. Possibly because of the aromatic C double bond C, one can have this kind of a stretching frequency in this particular spectrum. So now we have to check for the presence of NH2 in the proton NMR. The proton NMR characteristic peak corresponding to NH2 will be a D2O exchangeable peak. This is the proton NMR spectrum of this compound. The region between 3 and 8 alone is shown because all the signals are seen only in this particular region. You can straight away see a broad signal around 4.6 or so, and it says very clearly that it is a D2O exchangeable proton. So this 2 hydrogen intensity integration would correspond to an NH2 kind of a group. So the NH2 is confirmed by the presence of this broad peak, which is a D2O exchangeable group in the proton NMR spectrum also. The signal at 7.4 is looking like a doublet, and that is the same integration as this integration, NH2 integration. So this would correspond to 2 hydrogen intensity. So the number of hydrogens that we have, 2 hydrogens here, 2 hydrogens here, 4 hydrogen, and then 1 hydrogen in this particular region, which will be half of this integration. So there are 5 hydrogens present in this molecule, of which 3 of them are aromatic hydrogen and 2 of them of NH2 hydrogen. So far we have identified 2 bromines, NH2 hydrogen and 3 aromatic hydrogen. So totally 3 aromatic hydrogen means this is probably a tri-substituted derivative. We already have 3 substituent, 2 bromines and an amino group would be a substituent on the aromatic ring. So the possible structure is the 2,6-dibromoaniline is the structure. Why did we decide on 2,6-dibromoaniline? Because of the 7 Hertz coupling constant. The molecule has to be first of all symmetrical because there are only fewer number of signals in the aromatic region. Only a triplet and a doublet is seen, and the coupling constant, if you want to measure in this triplet, you take the gap between any adjacent line. This is a 100 megahertz NMR spectrum, so between 6 and 7 this is 100 megahertz, so this should be roughly about 7 or 8 hertz is the gap between these lines that are here. So an ortho coupling is what is responsible for the signals that is seen here. So the molecule should have ortho hydrogen. The molecular formula then it will be C6H5Br2N. The molecular weight 249, 251 and 253 matches with the mass spectral data that we have already seen. So this is the molecular structure of this particular compound, essentially deduced from the mass spectrometry first, identify the NH2 group and the presence of bromine, and the NH2 is confirmed in the infrared spectrum, and finally it is also confirmed in the NMR spectrum by the exchangeable hydrogen that is seen here. What gave the clue that it is a tri-substituted derivative is because of the presence of 3 hydrogens in the aromatic region. So 3 other positions must be occupied by substituents. We had already identified 2 bromines and 1 amino group, and these are the most likely substituent in the molecule, and we place them in the adjacent position, leaving the other 3 positions for the hydrogen, so that the HA can be split into a doublet by HB. So this is a HA 2 hydrogen intensity, and the HB is split by the HA into a triplet. So one can see the HB signal in the lower delta region. This is para to the amino functional group, so it is at a lower delta value, and meta to amino group will come at a higher delta value in this NMR spectrum of this particular compound. The 3 aromatic protons have to be ortho with respect to each other because of the 7 Hertz coupling which is seen, which is a major coupling that is seen in this spectrum that is see here. So symmetry considerations is important in the structural elucidation problem. This is an illustration of how a molecular structure has been decided based on the symmetry pattern or the substitution pattern that is deduced from the proton NMR spectrum of this particular compound. The fact that you have a doublet and a triplet seem to indicate that you should have 3 adjacent hydrogens ortho to one another in a symmetrical environment such that HB would be a triplet and HA will be a doublet as seen in the NMR spectrum. This is the carbon-13 NMR spectrum of this compound. There are 4 aromatic carbons in this, distinctly different aromatic carbons in this molecule. The ipso carbon, which has the electron withdrawing NH2 group, comes as a very low intense peak around 141 ppm or so, and the ortho carbons, which is ortho to the amino functional group, which will be the most electron deficient, the most electron rich in this particular case because of the nitrogen lone pair which can be delocalized onto the ring. So that comes at 2 around 110 ppm, 109 ppm or so, and the other 2 carbons, carbon number 3 for example, is the CH carbon which is coming around 130 or so, and the para carbon comes close to the ortho carbon which is around 120 or so in this particular case. This peak again is due to the presence of the chloroform CDCl3 peak, and this is due to the TMS peak at 0 ppm in this case. Let us move on to the next problem. The next problem, the molecular formula is given as C6H11ClO2. The degree of unsaturation is 1. So you can immediately conclude that this is definitely not an aromatic compound, because aromatic compound will be highly unsaturated in nature. A degree of unsaturation of 1 is probably due to a C double bond C or a carbonyl functional group alone can be accounted, and not an aromatic compound. So because of the presence of oxygen, we will have the routine check of the presence of or absence of OH, carbonyl functional group, and because there are 2 oxygen present here, one can check whether there is a carbon oxygen double bond as well as a carbon oxygen single bond stretching frequency in the infrared spectrum of this particular compound. Now the infrared spectrum is shown here. 1740 is a saturated ester peak. Carbonyl stretching frequency of an ester is what is seen around 1740 or so. Around 1000 there is a peak which is a fairly intense peak, which could be because of a C single bond O stretching frequency, and the broad intense peak around 1250 or so might be because of the carbonyl bending mode of this particular compound. The conclusion is that an ester group may be present mainly because of the fact that you have a 1740 signal and there are no OH signal, which is very important. No OH, so it cannot be an alcohol or an acid for sure. So it could be probably an ester kind of a functional group in this particular system. This is the mass spectrum of the compound. The molecular ion is not seen very clearly. It is very less abundant, less than 1%, which is not seen in the spectrum. So this is molecular ion 150, 152. Because of the presence of chlorine, you have 150 and 152 peak. What is important is the base peak, which is 43. It could be a acetyl group. So the molecule could be actually an acetate ester, fragmenting to give the acetyl group at 43 or so. The peak at 73 could be due to the presence of a COO CH2, CH3COO CH2. In other words, this is an acetate ester containing a CH2 group in the alpha position of the oxygen of the ester. So the remaining molecular formula, if you subtract the CH3COO CH2 from the molecular formula, the fragment gives you C3H6Cl. So we need to find out what is this C3H6Cl. Perhaps we can make use of the proton NMR spectroscopy data for the elucidation of the complete structure. The signal at 4.1 and 3.6, each of them look like a triplet, and it could be because of the presence of a OCH2CH2H kind of a X kind of a functional group that is present here. In other words, this CH2 will be a triplet because of the adjacent CH2, and vice versa. They are mutually coupled to each other, so they sort of give you a triplet and triplet kind of a functional group in this case. The acetate group, which we identified in the NMR spectrum, in the mass spectrum as well as in the infrared spectrum, is confirmed here. The singlet of 3 hydrogen intensity corresponding to this particular peak, which is a sharp singlet corresponding to 3 hydrogen intensity, could be a CH3COO group. So the presence of a CH3COO CH2CH2X is confirmed by the NMR spectrum. If you see the peak around 1.8 or 1.9, this multiplet here, this is an unresolved multiplet. It corresponds to 4 hydrogen intensity. So if you start looking at the CH2 here, which is a 2 hydrogen intensity and 2 hydrogen intensity, this would correspond to a 4 hydrogen intensity. In other words, the low chemical shift value tells us that these 2 CH2s are connected to 2 carbons at either end, and this CH2 is connected definitely to an oxygen because of the 4.1 delta value, and this CH2 is connected to some electronegative group, maybe chlorine, maybe an electronegative group. So OCH2, CH2CH2, CH2Cl is the group that we have identified from the NMR spectrum. This corresponds to OCH2, and this one corresponds to CH2Cl, and in between two you have 2 CH2s, which is a second order kind of a multiplet, is what is seen in the region of 1.9 ppm. So CH2, 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 CH2Cl is a fragment which is very clearly seen in the proton NMR spectrum of this compound, and the acetate group of course is very visible in the proton NMR spectrum. So this corresponds to the molecular formula which is given here as C6H11ClO2. This is C6C1, 2, 3, 4, 5, 6. There are 6 carbons. C6, and this is H11O2Cl. It fits the molecular formula, this particular structure. And let us see if the carbon 13 spectrum also confirms this particular data. This is a carbon 13 spectrum. The off resonance spectrum is given on the top trace, and the broadband decoupled spectrum is given in the bottom trace. And the carbonyl peak is very clearly seen around 172 or 173, which is labeled as 1. Then the next carbon would be the carbon that is directly attached to the oxygen, which is coming around 63 or 64 ppm, which is a triplet, so it has to be a CH2 kind of a carbon, which is very clearly seen. Then comes this one that is attached to the chlorine directly, that comes around 45 ppm or so, which is also a triplet. So number 2 and number 3 are taken care of in the spectrum corresponding to a OCH2 and a CH2Cl in this particular case. Number 4 and 5 carbons come at a lower delta value because they are attached to only a carbon, not to an electronegative element. So they come in the region between 25 to 30 in this particular region. Finally, carbon number 6, which is a terminal CH3, comes around 20 ppm, which is a quartet. These triplets are not very well resolved triplets. Nevertheless, they correspond to carbon number 4 and 5. This quartet is very clearly seen for the CH3 in the off resonance spectrum. So carbon labeled 6 is the carbon which corresponds to the CH3 of this particular functional group. Let us move on to the next problem. The molecular formula is given here as C9H10O2. The degree of unsaturation from this molecular formula is 6. It is possibly an aromatic compound because of a large degree of unsaturation that is present here. Because of the presence of oxygen, let us once again check the presence or absence of the OH and the carbonyl functional group in the infrared spectrum of this particular compound. This is the infrared spectrum of this compound. The carbonyl peak is very clearly seen at 1670. 1670 is corresponding to an alpha beta unsaturated or a conjugated carbonyl functional group, and 1600 peak, which is this particular peak here, corresponds to C double bond C, possibly because of an aromatic unit that may be present here. Now peak at 1000 and 1150 could be corresponding to a CO single bond stretching frequency. The molecule has two oxygen units, so it could be one carbonyl and another oxygen may be present as a C single bond O in this particular case. And the peak at 2900 to 2850 corresponds to the sp3 and sp2 type of CH stretching frequency, which is fairly intense in this region of 2800 or so. The mass spectrum of the compound is seen here. The molecular ion peak comes at m by z value 150, and 15 mass unit, which is the loss of a methyl group corresponding to 135, is seen here very clearly. And from 135, if you lose a carbon monoxide molecule 28 mass unit, you get 107, and from 107 you get the fragmentation peak, which corresponds to 77 in this particular case. So because of the presence, the loss of a methyl followed by a carbonyl, one can conclude that the molecule may be containing a acetyl kind of a group in this particular instance. In this particular case, an aryl COCH3 might be present in this case. So first loss of methyl group will give an acyl cation, and followed by loss of a carbon monoxide will give you the peak at 107. So we have to look for in the NMR spectrum peaks corresponding to methoxy. How did we decide there is a methoxy peak here? This is because of the presence of 107. 107 corresponds to a methoxy substituted phenyl derivative, and this is essentially 76 plus 15 plus 16 is corresponding to 107, for example. So one has to look for a methoxy group and an acetyl group in this NMR spectrum. NMR spectrum is fairly simple. This peak, which is a doublet of a doublet or an AB quartet as you want to call it, is because of a very characteristic feature of the para disubstituted aromatic derivative. So peak around 8.0 and 7.2, each one of them has 2 hydrogen intensity. It's already, the integration is given in the digitized format as 2 hydrogen and 2 hydrogen is clearly seen here. So this is definitely a para disubstituted derivative. Then 3.95 could be because of the methoxy functional group, and 2.5 could be because of the acetyl functional group in this molecule. So the molecular formula, the structure is solved very clearly. A para disubstituted derivative bearing a methoxy group and an acetyl group. In other words, it is a para-methoxy acetophenone is the compound. The para-methoxy acetophenone, the two chemical shift values of the aromatic units, aromatic hydrogen HA and HB, are very wide because one is adjacent to an electron withdrawing functional group, namely the acetyl functional group. That would correspond to the HB should be this particular one, and the HA should be this particular one. This is wrongly labeled, I am sorry about it. This is HB and this is HA. The HB is adjacent to the electron withdrawing acetyl group, and the HA is adjacent to the methoxy functional group, which should be at a lower delta value here. The methoxy signal itself comes in the region of 3.95 or so, and the acetyl signal comes around 2.5 ppm or so in this particular NMR spectrum. Carbon 13 spectrum should give 4 lines for the aromatics carbons. The 2 ipso carbons should come at a very low intensity. This is one ipso carbon which has a low intensity. The other ipso carbon is merged here. In other words, it is seen here as carbon number 3 is merging here. The one that has the methoxy functional group, which is an electron withdrawing oxygen substituted carbon, comes around 162 or so, and the other ipso carbon, which is only connected to a carbonyl functional group, comes around 130 or so in this particular case. And the two types of carbons which are CH aromatic carbons 4 and 5 come as intense peak, which doublet in the off resonance spectrum very clearly tells us this is corresponding to. Here again the ortho to methoxy will be electron rich in nature, so that comes at a lower delta value. The one that is adjacent to the electron withdrawing functional group should come at a higher delta value in this particular case. Finally, the methoxy comes at 55 ppm or so, and the methyl group of the acetyl comes around 25 ppm or so in this particular spectrum. And both of them are quartet in nature because of the CH3 groups that are present in the methoxy and the acetyl functional group. So in this module we have seen an interesting molecule which is a dibromoaniline. Without even having the molecular formula, we were able to solve the structure of this particular compound purely based on primarily mass spec, IR and proton NMR spectrum. And then we have an aliphatic ester, chloroester. Chloroalkyl ester is what is seen here. Here the important point is that these two CH2s are appearing as nice triplets, whereas this CH2s appear as a second order multiplet in the region of 1.9 ppm or so, and that was figured out from the proton NMR spectrum of this particular compound. Finally, an aromatic compound which is a para-disubstituted derivative with a nice para-disubstitution pattern, which is this particular pattern is seen, and the three compounds have been elucidated, structures have been elucidated from the spectroscopic data that is provided. Thank you very much for your attention.